So for those who are totally unaware of what we are doing, we are on chapter 6. And the chapter is momentum and collisions. Right?
Yeah.
And you have already done everything about momentum, mass times velocity. And what causes momentum? Or what changes the momentum of an object?
Force.
A force applied for a short period of time. What do you call that? Force applied for a time. What do you call it?
Change in moment. Impulse.
No,
Impulse.
Yeah.
Impulse. Force times time is called no talking. When I ask questions, answer, otherwise no talking. Force times time is impulse. So when you apply an impulse on an object, it causes change in momentum of the object. Is that clear?
Yeah.
Force times time is impulse, which causes change in momentum. One of the questions in the homework that some of you struggled and you started emailing me about, I have no clue how to do this question. And one of that question is this. It said an impulse of 64 Newton second is applied on a 75 kilogram object or something like that. And the question was asking, what is the change in its momentum?
Same thing.
It's the same thing. 64. You don't have to do anything there. Because I gave you impulse, 64, and I'm asking what's the change in momentum. It is the same thing. Instead of that, some of you are multiplying 75 times 64, dividing it, and trying to do all sorts of things to get some different answer, not 64. Okay, so if your concept is clear, that force times time is change in momentum, that should not go wrong at all. All right, so we will do some more exercise today on the same concept with an additional concept. So we did momentum, change in momentum, impulse, concepts and all that all covered. Now can you turn to page 194 from your textbook? Page 194. Cameron, I believe that you've not got your textbook yet.
Yeah. I tried to get it yesterday, but Mr. Dill wasn't allowed.
You can just hold on for at least 2-3 months and the semester will be over.
True.
Yeah, and then after that you don't have to worry about buying a book, right? I want your book next class. And also calculators, you must have a calculator, so bring it out and keep it ready so that you are going to work together. Only when you work in the class, you will know exactly how to tackle these kind of things when it comes in the form of tests or quizzes. I think I gave one already. Check if there is one little one here. Don't knock that. I don't know. Check. So, you decided to keep talking?
Oh, no.
Just making sure. Page 194. I'm going to work through some of these questions so that you will get the proper directions of how to do these things. This exercise is slightly different from the previous one, slightly. So let's see how it goes. I'm looking at the sample problem. So I'm going to read the sample problem and I'm going to show you how to look at it. A 2,240 kilogram car traveling to the west. Every word is important. When they say west, don't forget it. Is traveling to the west, slows down uniformly from 20 meters per second to 5 meters per second. Question is, how long does it take the car to decelerate if the force on the car is 8,410 newtons to the east? And then there is a second question that follows after that. We'll talk about it. So what do you do first? Yes.
Do you have an extra pencil?
Okay. So this is a car which is 2,240 kilograms, and this car is moving to the west at 20 meters per second, and it slows down to 5 meters per second. It slows down to 5 meters per second, and this is because there is a force acting to the east of 8,410 410 newtons. This is what they have said in words. I'll read the question again and look at the picture that will get you an idea. A 2,240 kilogram car traveling to the west slows down uniformly from 20 meters per 20.0 meters per second to 5.00 meters per second, 368. How long does it take the car to decelerate if the force on the car is 8,410 newtons to the east? So I've shown the east this way, west that way, right? And the question is asking for what? Time. And here, what you do is, we're going to use the impulse momentum theorem. Basically, F times T, is change in momentum. F times T is change in momentum, which is equal to mass times final velocity minus initial velocity. This is something that we already know. Right? Right?
Yeah.
Any computers open? Close them if you are. So this is impulse causes change in momentum, which is this. So we're going to use this theorem. So let's substitute. What is the force?
8,410.
8,410 times time. We don't know the time. Time is a question. Time is the question. Is equal to change in momentum, which is this. What's the mass of the car? You see, it's very important that you write the equation down and then substitute the numbers very faithfully. What is VF? VF, final velocity?
5 meters per second.
What?
5 meters a second.
That's where things go wrong.
Was it 15?
That's where things go wrong. I read the question so clearly.
Oh.
I drew the diagram of the question. And now you're making a mistake. What is the final velocity?
Negative.
-5. Very good.
Why?
It is -5 because it's going to the west. How do you differentiate west and east? By signs. You have to put the signs. Because it said west, you're taking it as negative. So -5. And this minus sign is the same minus sign. I'm not changing it. Now what is VI? -20. And this is where things can go wrong, so I'm letting you know. Don't be careful when you substitute stuff. And then after this, it's only clean up. This is 2240 times. What is this? What is negative of negative?
Positive.
Positive 20, -5, 15. And then now you work it out. So T is equal to how much? Calculate. How much is T? Time.
Negative 1.3.
Time can never be negative.
Oh, time.
No, there's no negative sign here for
4
you.
seconds.
4.00 seconds, correct. So time is 4.00 seconds, and we got the answer. And why 4.00? Because there's a 3 sig figs over here. Is that clear? Now let's go to the second part of the question, which says, how far does the car travel during this interval, during this thing? So how far does it go as it is slowing down? How far does it go? So we want x.
60 meters.
So we want x. What do we have? We have time, which is 4.00 seconds. We have initial velocity, which is -20. We have final velocity, which is -5. And you want x. What can you do to get x? Is there any idea? Equations of motion. Pick up an equation of motion which involves only these variables. Which equation is that? Something that does not have acceleration. Something that is not have
Is
force.
it X equals VF plus VI times
X is equals to VF plus VI divided by 2 times time. This is your equation. That's the equation. Now plug in. Just plug in faithfully. What is VF?
-5.
-5 plus negative 20 divided by 2 times 4.00 seconds. So negative 5, negative 20 divided by 2 times 4. Calculate and tell me the answer in 3 seconds again.
49.0.
Negative 50.0. Right, negative 50.0 meters. Now, what does that minus sign imply?
West.
Yep. So you say 50 meters
To the west.
to the west. Now, the only difference that you see in the problem solving is this step. In this exercise, this is the only thing that's different, right? You already know this kind of thing. But this is the only thing that is slightly different in this exercise. Is that clear? Everyone? Now look at the first question on page 195. This is, don't have textbook. You must have a textbook. And sit together so you can also share. Look at the first question on page 195. It says, how long would the car in sample that we just did take to come to a stop from the initial velocity of 20 meters per second to the west? So they're asking you, how long would it have taken if it has to come to a stop? How long? So now the question is, how much time? So what is going to be the difference on this board?
Just plug in 0.
Exactly. So this will go and you put 0. So what will this number be? Huh?
That'll be -1.
No, it will be negative of negative 20, which is
Positive.
positive 20. And so this time is not 4 anymore. What is it? Calculate.
0.
What?
0.
I forget I said anything.
You said
The
the
luck
luck
is
is
right.
right.
I thought he was asking.
I was asking.
You weren't
even close.
Oh, well, never mind.
So what we have changed over here is we put 0 in place of negative 5 because it is starting, and then recalculate. How much is the time? Calculate. This is your time to calculate.
5.33.
5.33. So 5.33 seconds is your new time. And that is the time taken to stop. And then the question follows, how far will it go before stopping? So basically you need to find out this whole distance. So, yeah, 5.33 is your new time. And all the rest are exactly the same. Plug it in.
Well, no, they're not.
No.
VF would be 0. Yeah, the VF would be 0. Right?
Oh, VF is 0, correct. VF is 0. So now recalculate, and this will change to 5.33. And now recalculate and find out how much this is. Yeah.
Negative 53.3.
Negative 53.3 meters is correct, and that means 53.3 meters to the west. Is that clear? Now I want your attention to question number 2 on the textbook. And I want you to do it, and I'll just come along and see how things are going, and I'll work it out on the board if necessary. So this is your time. Draw properly, just like how I showed you through an example, and then do that exercise. All right, so I'm showing the work over here, now pay attention. No, you don't need to turn it on. Brian. Turn.
Right.
Alright, I'm going to show the same way, the work the same way. Now, have you drawn a diagram at all? If you have not drawn a diagram, that can be the first cost. A 2,500 kilogram car traveling to the north is slowed down. So, here is a 2,500 kilogram car traveling to the north at 20 meters per second. So, I've drawn everything there. And is slowed down by a 6,250 Newton braking force acting in the opposite direction. So there is a braking force of 6,250 newtons. What is the final velocity of the car after a time of 2.5 seconds? So time, no talking, I said clearly. You have the time to do it, and I'll pay attention. Substitution time. How much is force?
6,250.
It is negative 6250. Now, if you fail to put the minus sign, then what's the point in drawing an arrow downward?
That's also why I'm wrong.
That is why everybody was wrong.
We're slow.
Because this one times 2.50 seconds is equal to mass 2,500 times VF, we want it, minus VI is a positive 20. VI is a positive 20, right?
Yeah.
So
Yes.
this minus sign is the same as this minus.
Yeah, it's did the 20.
Now substitution, like calculations. So this is minus, multiply this, you'll get 15,625 equal to 2,500 times VF minus 20. Now from here, it's an algebraic skill. So what do you do from here? You divide both sides with 2,500. And so and that gets knocked out. And if you divide this with this, you get negative 6.25 equal to VF minus 20. And now you know how to do it from there. Add 20 to both sides. So add 20 to both sides, plus 20, plus 20. So you get positive 13.75. Now this needs to be rounded up. So your final answer is 14 meters to the north. Meters per second. 14 meters per second to the north. That is your final answer for the final velocity.
I would have got it if I had a calculator. You got a calculator in your table. Yeah, I can't even see.
Everyone has calculators in the brain, so you should use that at least.
Hey, bro, that's not a cause.
Mr. Sim, in the class, can they give you a bunch of random numbers and then you divide it?
Oh, yeah.
Yeah, come on, Mr. C.
Now this was an easier one. That's why it was easy for me to do it. Much faster. Because you see this. Multiplying by 2.5 is the same as multiplying by 10 and dividing by 4.
Oh.
So all I have to do is add an extra 0 here and then divide this with 4, which makes it easy.
Mr. Sam, divide 1,264,000.
Yeah, that's what I said. There are some shortcuts that you can actually go and just use your head and get it. You don't have to use a calculator to multiply this. Isn't it much easier to multiply by 10 and divide by 4?
Yeah.
Simple.
Yeah, I can figure that out.
No.
No? That also is difficult? Okay.
That's a lot to think about.
Now the second part of the question. How far does the car move during the 2.5 seconds? You should be able to do that equation of motion. Go ahead. Yeah. 42 meters to the north.
You need to give me a 10.
Yeah.
He was already up there because you have the textbooks. You can go ahead and work it out. If you've done the second part, go ahead and do the part C. Yeah.
8 seconds.
Correct. 8 seconds. Wonderful.
Dang it. What was B?
B was 42 meters to the north. Everyone should be able to do it.
What was the time that you said? What was the time that you said for the part 2?
Part 2, it's not the time, it's how far.
What's 3? I mean, part C.
What was it? 42 meters. So for part 2, use this equation. X is equals to VF plus VI divided by 2 times time.
2.5.
Stop talking. So X is equal to VF. Oh, use this final velocity, not this one. This is a rounded number. Don't use this.
Oh, okay.
So 13.75 plus 20 divided by 2 times 2.50. If you do this, you should get around 42 meters.
Could you do that in your head?
Yeah, same thing. It's the same thing, multiplying by 2.5. So this is 33.75 becomes 337.5.
This is
And then you divide by 2.
You think if someone just read
Oh,
you this
you're-
equation,
Divide by 8, huh?
you think if someone just read you this equation and without writing anything down, you do the whole thing in your head?
Okay.
Jeez, that's impressive.
Alright, so you got the answer, 8 seconds?
Sorry to hear about
Yeah.
that.
Can you work that out, please?
So wait, you used the FT equals change in momentum 2 times, right?
So did you get this 42? Yeah.
2 separate times. What?
No. For the last part, pay attention. The question is asking how long does the car take to a complete stop? That means this is the initial velocity and the final velocity is not this, but it is 0. So your this is going to be the question. For the last part, this is what the question is asking you to find out, and this is 0. That's it. Rework it. So negative 6250t is equal to 2,500 times negative 20 is negative 50,000. So t equals negative 50,000 divided by negative 6250, and the answer is 8.00 seconds. Got it, Henrik?
Mr.
Yeah.
Tuner, I have a question.
Take it a while.
So what I did is, I don't know if I did it correctly. I put in 2,502 to get 5,000, 50,000.
Oh, no.
Or sorry, I meant to put 20 there. It's just a miss.
20, okay.
But I calculated it.
Okay, so you
And
got
then I-
no, this is not the equation.
Yeah, and then I put negative 50,000 on this side. I did the FT.
Not tucked in the other one.
But can you do that where you use it twice and just change
No,
it?
you just did the same thing. You actually found out this first, and then after that you put it. I'm just doing it all. Conservation of momentum. Now this is a slightly different one that you are actually going to learn now. What's the meaning of the word conservation? Saving or keeping the same, right? Keeping the same. That's basically the conservation. Now, conservation of momentum means momentum should stay the same. Now, this conservation of momentum relates back to the first law of Newton. What is the first law of Newton? Anything that is moving with a velocity will want to continue to move with the same velocity unless acted on by external unbalanced forces. Anything will want to continue to have the same velocity. That's first law of Newton, which you already know. Conservation of momentum is not different. It is the first law, once again, put in a slightly different way. What is it saying? Conservation of momentum says the momentum of an object will stay the same unless acted on by external unbalanced forces. Make sense? So if I'm taking this, if I take this part and push it on this rail, I gave it a momentum, but what happened finally? What happened to momentum? Why did the momentum drop?
Friction.
Friction becomes the external unbalanced force. So because friction is there, it is stopping. Friction is there, that is why it is stopping. Now, if friction is not there, what should happen? It should keep going with the same momentum. Yeah, momentum. It should continue to go with the same momentum. Like in space, if I throw this like this, it should keep going the same way. There's no change of momentum that is expected. So it should continue with the same momentum.
So what if you have like two opposite magnets? You got like how they pull against each other.
And then you're talking about magnetic levitation something?
Yeah.
Yeah, if you can magnetically levitate stuff and then if
It
you
would
try to
go on
move it,
forever.
it will be like pretty good. But still air resistance is something that cannot be, remote. Air resistance is something that cannot be remote. So I'll show you something here. What it should do. Now this is, those air tracks. You see the tiny holes and air comes out from it.
Oh, it's like a
So now there is, now if I push it, it continues the same momentum. The momentum is not supposed to decrease, but I can see still there's a decrease, right?
Like an air hockey table.
It is still cutting off.
What? It is.
Yeah, I said that 30 seconds.
Oh, I didn't hear you. Line.
Now, why is it still slowing down?
Air resistance.
Because of air resistance. You know, it's jet of air coming out, so it is still cutting off air, and so there is still air resistance. You can't completely get rid of it. You can't get rid of it completely. So air resistance is the biggest, external force that can come and stop many things, right?
Make that
But momentum is definitely conserved. So if I'm going to use some other chord,
Oh, yeah, big car.
good.
Something stop moving.
Yeah, it is doing pretty good, but it is still losing energy. It's still losing energy because air resistance. Now, momentum conservation is not for just one object, even for multiple objects. Like, for example, your pool table. If you hit one ball, that ball hits the next one, passes on the momentum to the next one. So probably the first one stops and the second one shoots off, right? You've seen it?
Yeah.
Which is, why is it happening? Because momentum has to be conserved. It cannot be lost. It cannot be created. Momentum, if it is there, it is okay. Momentum can be created by an external force, correct? Like when you apply impulse. But any momentum that's created because of an impulse should not be lost. So if I'm creating momentum here, it should be sharing. They're sharing momentum. So momentum is not for, conservation of momentum is not for one object, for multiple objects. Say, so for a system of objects, momentum, total momentum is conserved or stays same. In the absence of external unbalanced forces. If external unbalanced forces are not there, then the total momentum should stay the same, should not be different. And you have seen this earlier.
Classic.
Yes.
What is it called?
Newton's cradle.
Newton's cradle. Yesterday someone said Newton's balls.
Who said it? Exposed.
Alright, so now what is to be seen over here is this: they are made of steel. Now why steel? Because steel is one of the most elastic substances. It is very elastic, which means it will be able to deform and get back into normal shape very quickly, unlike rubber. Rubber is more flexible, but steel is more elastic, and I'll talk about elasticity later. But steel is used here. So what happens when I actually pull out one of the ball, if I'm pulling one of them and letting it go, So when I let it go, as it swings down, it is losing GP and gaining kinetic energy and therefore gaining momentum, right? So what happens is it goes and hits the first one and transfers its momentum to the first one, but the first one is blocked by the second one, so it passes on to the second one. And the second one is blocked by the third one, so it passes. And finally, the last one picks up the same momentum and goes. And on its return, it'll do the same thing backward. So that's what you can see here. So the middle one, like this is just taking part in the transfer, but it is not actually moving much. Instead, if I take two of them together, that means it is twice the momentum. Right? You can see two of them taking off on this side. They have to take off because momentum should be conserved. Yeah.
Is the more mass, the more momentum?
Yeah.
Okay.
Mass times velocity is momentum.
Yeah.
So if I take three of them together, you can see how three of them are moving.
Four.
Yeah, sure.
Oh.
Hey. Do five.
It's very cool. Five is just going to swing like a pendulum. Now, what if I take one from here this way and one from here this way?
Ooh.
So what's happening is each one is passing its energy to the next side, next one, and you can see that is going on. Now, what if I take two from one side and one from the other side?
And make the other one go.
2 and 1 and 2 and 1. You can see that. Like I'm taking two of them off, right? And one of them here. So when this one comes and hits like that, only one will get dispatched here. But it'll keep switching. That's interesting.
Well, they're switching like that.
You see that?
How long will it go for?
Only sometime. Because again, energy is slowly being destroyed by resistance and all that stuff. So
Do 3 and 2.
3 and 2. It's pretty interesting to see how momentum.
What if you don't drop them at the same time? What would happen? Like you drop one a quarter second later.
We can try.
So like,
Yeah, there's nothing wrong with trying.
you like release, you release one before the other. That's what I'm saying. Oh, that's
pretty cool.
yeah, it like clicks different.
Looks like a nice rhythm there.
Yeah.
Make a song with this.
Exactly. Rap.
Yeah. Like a YouTube rap.
Let's try this.
YouTube channel.
Beats by you. Senior made it.
It looks like almost magnets.
Yeah. Alright, so that is conservation of momentum. Now, what are we going to look into conservation? Why are we looking at a conservation of momentum? Because there are a lot of things that are colliding with each other, right? Truck and car collide with a car. You know, when you are, bumper cars bumping into each other. In all these kind of collisions, momentum is conserved.
So wait, if you hit a bumper car, it'll go forward, but if you come at each other, then
They'll just bounce back. Yeah. It depends on which one is heavier. Look at this now, for example. Look at this. If I'm going to turn on both of them, like I'm going to move both of them together. Like imagine like two football players. You know, when I talk football, go look around. Yeah? When imagine there are football players. One is a heavier football player and the other is a lighter football player. And they're both running into each other and bouncing off. So they're both running together with the same speed. But then who's going to be affected by that? Look. He's not affected much. This one is affected a lot. Doesn't matter. I'm good. Okay.
What is it? What happens if you send that one faster now?
Faster than that?
Yeah, so like that one's slower, but you send
But
that
still,
one
this will be the one which will be affected.
Really? Let me see it.
Yeah.
Just throw that one like twice as fast as Me versus Patrick over here. Yeah, Patrick.
Now this is what's going to happen. So it almost lost all its energy. Fine.
Dude,
So how do you deal with
SKM at 360.
collisions of any kind? As you can see, the
wait.
total momentum before should be equal to the total momentum after. That is a conservation. So total momentum before
Literally every class.
is equal to the total momentum after. It can be for two objects, one object, it can be for anything. So let's say, for example, if I have a cart which has a mass of m1, and it's a cart that has a mass of m1, and it is moving with an initial velocity of vi1, and if it goes and collides with another car of mass m2, which is moving with the velocity vi2, like think of two cars, one going, the other one's going, so they come and hit.
Are they going head on or are they going?
No, back to back. Like suppose somebody's going in a bumper car like this, and you go in a bumper car faster, and then hit. So what will happen to you? You will have a new velocity, and that person will have a new velocity, right? So after the collision, the mass m1, the cart m1 is having a new velocity, final velocity, and the cart m2 will have a new final velocity. But the total momentum should stay the same, right?
Yeah.
So what's the momentum of this one?
It has to be faster, right?
Now what is the momentum like in terms of these letters? What is momentum? Momentum is given by what?
P.
P is what? Mass times?
Mass times velocity.
So mass times velocity. So it's like m1 vi1. m1 vi1. And what's the momentum of this? m2 vi2 should be equal to m1 vf1 plus m2 vf2. This is an equation for momentum conservation for two objects. Like if these are bumping into each other, the sum of these two should be equal to the sum of those two.
Can we write down like the carts, conceptualize this?
Yeah, the total momentum of the cars before is equal to the total momentum of the cars after collision. So it's like mass times velocity. Now what if after the collision they stick together? After the collision they stick together.
But they would be just,
They have the same momentum.
it would be the same.
No, they'll have the same velocity finally, right? Imagine there are two football players, again, running into each other for a tackle, right? And they're both moving the same speed, but one is heavy, one is light. One is heavy, and the other is light. They're both moving together with the same speed, but they tackle each other, like hug each other, okay? So they run into each other, and then tackle. What happens after the tackle?
They bounce off.
They'll go this way. They'll go this way. Why? Because, now, imagine they're both equal weights and they run into each other for a tackle. They stop. They stop. Because momentums are going to, go backward. So, there are two kinds of collisions. One, when they bounce off, just like what you saw here. It just bounces off. And the other one, they can get stuck. So, if a truck comes and hits a car, you can have them kind of bouncing off, or sometimes, the worst cases, it can just get tangled into one. Right? So let's look at a numerical example here. A numerical example. So I'm going to show you, this is a numerical example. So let's say this is a 25 kilogram cart. moving at 10 meters per second, right? And this is a 40 kilogram cart at rest. So one is a 40 kilogram cart at rest, and this is a 20 kilogram cart, 25 kilogram cart moving at 10 meters per second. And let's say after the collision, they get stuck together. They get tangled like that. And once they get tangled, they will have a final velocity together, right? Common velocity. So there is a final velocity. How much? What will be the final velocity? So to do this, what you have to do is find the total momentum before. What's the momentum of this? 250, correct. Multiply mass times velocity to get the answer. 250. What's the momentum of this?
0.
So what's the total momentum of the whole thing? 250. Should be equal to the momentum of that.
So that's 250.
What is the total mass of the whole combination?
65.
And the only velocity is that. Can you find how fast?
3.8.
So VF is 3.8 meters per second. So if this really happens, this is the final velocity. This is the final velocity. Now these kind of calculations are normally done even by cops. If someone actually is driving a car and bumping into a stationary car and then drag the car a certain amount of distance, the cops will come and look at all the tire marks and do the measurement of how far, use the coefficient of friction of the road with the tires, and then he'll be able to find out how fast, and therefore he'll be able to work backwards and find out how fast he came and hit. So you can't tell lies over there saying, I was driving at 25 miles per hour. No. He will calculate backwards with all the measurements, and then he'll say, no, you were driving at 60 miles per hour, so you lost your insurance as well. You understand what I'm saying? So calculations are done. Yeah, so the cops will have to learn a little bit of physics too. Okay, so they need calculations. And that is why they say, when you are in an accident or something like that, stop where you are, because those positions are very important for them to come and analyze the situation.
What if you're in the wrong? Then you want to move.
You're not supposed to. If you move, that means the blame comes straight away on you.
Physics is everything.
Why are you getting up? Stay.
You got more to learn.
I'm
You
just
got 5
stretching.
minutes left.
I was just stretching.
Exactly.
What are those 400s made? Underboard.
That's money.
Well, I know. I don't know if you mentioned anything. Like it was your first paycheck or something.
Jack, you got rid of lunch?
Yeah.
All right. Shh. Is this clear?
Yeah.
Now, do another question. One more question here. Whose phone is this?
Yeah, there's a phone back here.
Well, I said 130.
It kind of looks red.
Is it kept for charging? Here we go. So here is a car moving 10 meters per second. This is moving slower, 8 meters per second. What will be the combined velocity of the whole thing? What do? Do the same thing. What's the momentum of this before impact? Now what's the momentum of that before impact? What do you say?
It's negative.
Negative 8. Negative 8.
320. Negative 320.
So it's negative 320 is equal to 65 VF. And that will tell you negative 70 is equal to 65 VF. And that tells you VF is 1.07 meters per second, but minus. What does the minus say?
West.
It goes this way. So after the impact, it goes this way. No matter, even this is faster, but no use.
Going left.
It has got more momentum here, so that's what's good. One last example. One last example. What is that? Okay, gun. A 1 kilogram gun. And what is this?
bullet.
A bullet, a 25-gram bullet.
Davidson.
So you have the gun and the bullet. They're both initially at rest. So what's the momentum of the whole thing before firing?
Yeah, hard.
Zero.
Now after, some of you are just fooling around here. After the gun is fired, now it becomes two objects separate. Here is the bullet.
Get the recoil.
And let's say the bullet is going at 250 meters per second. What is the velocity of the gun after the impact? So let's see. 0 on this side is equal to 1 VF, momentum of this, plus 0.025 times 250. And if you work it out, 0 equals to VF plus 6.25. So VF comes out to be negative 6.25 meters per second. What does a minus sign indicate? That the gun moves backward. What do you call it? Recoil of the gun. So why does the gun recoil backward? Because of conservation of momentum.
Wow.
In order to conserve momentum, when the bullet gains a positive momentum, the gun has to get a negative momentum. Is that clear?
Yeah.
Yes, sir.